Hello everyone, we will start with chapter 9, polynomial rings. Okay, so everyone watching this video knows what is a polynomial, the degree of a polynomial. For example, a polynomial is a structure like a0 plus a1x plus till anx power n. A0, A1 till AN belongs to some ring R. Commutative ring, not commutative, R is a field, whatever. Okay. The ring of polynomial is R of x. R of x is a ring under the addition, the usual addition and the usual multiplication of polynomials. The identity element is the polynomial p of x equal to 1, and the zero polynomial is the polynomial p of x equal to 0r. Okay, so everyone is watching this video must be familiar with these concepts, and is called the degree of the polynomial p of x, provided that an is different to 0, of course. If an is equal to 1, an is the leading entry. If an is or leading coefficient, if an is equal to 1, then this polynomial is said to be monic, called monic polynomial. Okay, so I will not prove that r of x is a polynomial under the usual and addition and multiplication of polynomials that we know from high school. You can do it as an exercise. I will start with the division algorithm, so theorem. Let f of x and g of x belong to f of x, where f is a field, of course. From now on, f denotes a field, where f is a field, and the g of x is a non-constant polynomial. Then there exists a unique polynomials q of x and r of x in f of x, such that f of x is equal to q of x dot g of x plus r of x with r of x equal to 0, or degree of r of x less than. So if r of x is not equal to 0, the degree of a non-zero polynomial is well defined, and degree of r of x in such case is less than degree of g of x. Okay, this algorithm most of us saw it in high school, secondary classes, so we will prove it now. This theorem, you should notice that this theorem is only is true if f of x and g of x belongs to polynomials, are two polynomials with coefficients that belongs to a field. Okay, this is a very important assumption. Okay, without this assumption, the theorem or the result is not true. So proof. Let S be the set f of x minus hx dot g of x, such that h of x is any element in fx. Now it's clear that S is not empty. Why? F of x is an element of S, so S is not empty. Now, if 0 belongs to S, nothing to show. Why? Since we could write the f of x equal h of x dot g of x for some h in f of x, and r of we take h of x is a q, we call h of x a q, and the remainder is or r of x is equal to 0. By the way, r of x is called the remainder, and remainder polynomial, and the q of x is called the quotient polynomial, or the quotient of the division of f of x by the polynomial g of x in the ring of polynomials f of x. Okay, so if 0 belongs to S, nothing to show. Suppose that suppose that 0 does not belong to S. So each degree or any polynomial in S, the degree is defined and it's greater than or equal to 0. So we choose a polynomial. They are all non-negative. They are all greater than or equal to 0. And the degree is defined, of course. So we can choose r of x of minimal. R of x belong to S of minimal degree. Now r of x is in S, so r of x is equal to f of x minus q of x dot g of x minus h of x dot g of x. I will call hq here. Okay, so that's the definition of S. R of x can be written as f of x minus hx. I will call it q of x dot g of x. This is equivalent to say that f of x is equal to q of x, g of x plus r of x. Okay, so the existence of Q automatically holds, the existence of R automatically holds, but we need to show that the degree of R of x is not equal to 0. Sorry, the degree of R of x is less than or equal, want to show less than or equal, less than, sorry, strictly less than the degree of g of x. Now the degree of r of x to show that the degree of r of x less than the degree of g of x, so we suppose the contrary. Suppose degree of r of x equal to m greater than degree of g of x greater than or equal degree of g of x, which is n. And you may write r of x equal b0 plus b1x plus still bmx power m. Of course, bm is not equal to 0. Q of x or g of x is equal to a1 a0 plus a1x plus etc plus anx, where an is definitely different from 0. So now m is greater than or equal to n. We have f of x minus g of x multiplied by q of x plus bm over an. bm over an, what we mean by bm over an? Bm dot an minus 1. Bm over an is bm dot an power minus 1. An is not equal to 0. To make sure that am minus 1 exists, we need to work in a field. Okay, that's the important of using fields in this theorem, as I mentioned before. So let's complete. Bm over an dot into xm minus n. simplify this term here, or this expression, you find that this is equal to r of x minus x power m minus bm x power m plus terms of lower degree, of degree less than m. Okay, terms of lower degree. Lower degree, I mean less than m. Okay, r of x minus bmx power m eliminates this term here from r of x. So we got a polynomial. This whole expression is a polynomial of degree lower than m, and m polynomial of degree lower than m, and also an s. A contradiction, since we choose as r of x an s of minimal degree. This implies that the degree of r of x is less than strictly than the degree of g of x, okay, as required, as desired. Now we turn to the uniqueness. Suppose that f of x, suppose f of x can be written as q prime x g of x plus r prime of x equal q of x g of x plus r of x. So this implies that q of x minus, of course, suppose q prime and q are not equal, r prime and r are not equal, okay? Or suppose only q prime and q are not equal. Suppose that q prime and q are not equal, so this difference is not equal to 0, and the degree of this difference here is well defined, times g of x is equal to r prime of x minus r of x. Now the degree of this term is defined, the degree of g of x is defined, is well defined, so the degree of the product is well defined, and the degree of r prime of x minus r of x is well defined. Moreover, the degree of r prime minus r is equal to the degree of this term here, which is definitely greater than or equal to the degree of g of x. Then the degree of r prime of x minus r of x is greater than or equal to the degree of g of x. But we know that each one of these terms, r prime and r of x, has a degree lower than that of g of x, which is a contradiction. And our assumption that q prime of x minus q of x different than 0 is wrong, and q prime of x is equal to q of x. Now q prime of x is equal to q of x implies automatically that r prime of x is equal to r of x, and the uniqueness follows. Okay, so this is the division algorithm, a very important result in abstract algebra. A corollary: let f be a field, and let f be a field an element alpha in f is a root of p of x, of p of x, an element, a polynomial in f of x, if and only if x minus alpha is a factor of p of x in f of x. Proof: the second direction is trivial. The first direction, we will use the previous theorem. P of x can be written as x minus alpha into q of x plus r of x. Okay. Now, of course, using the previous theorem, with degree of r of x equal to 0, sorry, degree of r of x less than degree of x minus alpha, or r of x equal to 0. If r of x equal to 0, then nothing to show. Then nothing to show. If not, then r of x, p of x equal x minus alpha q of x plus r of x, okay? So degree of r of x, if r of x not equal to 0, degree of r of x must be less than the degree of g of x here is x minus alpha. So degree of r of x must be equal to 0, r of x must be constant, okay? So this polynomial here is constant. Now we have, by the assumption, p of alpha equal to 0, and p of alpha is equal to r of alpha. So this constant is equal to 0, okay? So we showed that r of x is equal to 0. And x minus alpha is a factor of p of x and f of x as required. Now another corollary, alpha is a field, sorry, let alpha be an element in a field. A non-zero polynomial p of x and f of x of degree n have at most n roots. So if we have a polynomial p of x and f of x of degree n, then p of x have at most n roots in f. Okay, direct consequence of the previous result. I'll not prove here.